In an interior Alaska winter, cold entered through every surface and every draft. Fingers stiffened. Damp clothing cooled against the skin. Sleep became harder as the room lost heat. A Koyukon Denaa family could not spend the night feeding a large fire without pause. The modest central flame mattered. Every piece of fuel had to remain useful after it caught. If you look past the flame, the first working part was overhead. Timber covered with birch bark, dry moss, and earth. The obvious response was more wood. A larger fire released more heat, but it also consumed more oxygen. Outside air had to replace that oxygen. Smoke and hot gases had to leave through the opening above the hearth. As the fire grew, fuel disappeared faster, and more warmed air left the room. If the shell leaked rapidly, extra flame could balance the loss for a time. It could not reduce the loss itself. The boundary of the house did that work. In physical terms, birch bark would have reduced air movement through the frame. Dry moss held pockets of still air. Earth added depth between the occupied room and the wind. If you trace heat rising toward the roof, each layer lengthens and slows its path outward. The layered shell reduced the rate of heat loss. The hearth no longer had to match the weather at every moment. It replaced energy that escaped more gradually. You can see the result in a longer interval between pieces of wood. A person returns to the platform while the structure retains warmth around the family. I'm Birch. Watch where that remaining heat goes. The shell made the fire less demanding, but it created a new problem. Smoke and combustion gases still needed a high route out. The flame also needed replacement air. A broad doorway beside the family would have carried winter wind across the occupied space. The entrance geometry allowed another path. A person came through an outer opening, descended into an antechamber, and crossed a low passage before reaching the main room. The turns interrupted a straight line from the weather to the hearth. Above the central fire, heated gases rose toward the roof opening. As they left, outside air could enter through the lower passage and approach the flame. That geometry allowed a vertical air circuit. The hearth could receive oxygen. Smoke moved upward. Much of the incoming flow stayed near the entrance and floor. A person could tend the fire, step back onto a platform, and continue a task away from that moving air. Keep the cross-section fixed. The entrance remains low at one side. The hearth stays near the center. Platforms line the sides above the lowest floor. The roof opening remains over the fire. If you follow the flow, air enters low, approaches the hearth, warms, and rises. The house does not stop air movement. Its geometry directs that movement through specific parts of the room. That direction exposed another problem. Replacement air reached the bottom of the room before the fire warmed it. The lowest floor, therefore, held the coolest moving air. A sleeping surface, placed there, would meet the incoming draft before the air reached the hearth. The side platforms changed that relationship. They raised sitting and sleeping surfaces above the lowest floor while leaving the center open. From that height, a person remained near the fire's radiant warmth. Colder replacement air moved below and inward. Smoke and hotter gases continued above toward the opening. Look from the entrance toward the rear wall. You can see 3 vertical zones without changing the drawing. The lower zone carries incoming air. The center holds the hearth and the people. The upper zone carries smoke and warm exhaust. Daily life occupies the band between the two flows. That placement changed ordinary work. Hands could repair a strap or prepare food away from the entrance passage. Damp garments could remain near warmth without blocking the hearth. Someone adding wood entered the center, then returned to a platform instead of staying on the coldest floor. Human activity added moisture. Breathing, cooking, damp clothing, and the ground released water vapor. Warm air carried part of that vapor upward with the smoke. The roof opening did not make the room dry or smoke-free. Its narrower role was to receive the rising flow above the hearth. If you trace the circuit from below, replacement air enters through the passage. The hearth warms it. Smoke, warm air, and part of the moisture rise toward the high opening. The shell slows heat crossing the roof and walls. The room now has a low intake path and a high exhaust path. The room did not maintain one uniform temperature. Near the entrance, the lower floor remained cooler. Directly above the hearth, gases were hotter and less suitable for occupation. Along the raised sides, air moved more slowly and radiant warmth remained available. The house needed a usable human zone, not identical conditions in every corner. At first, the side structures look like beds and benches arranged around a fire. Their position reveals a second function. In physical terms, the platforms created thermal zoning. Their position placed human bodies above the coldest incoming air and below the main smoke route. If this Koyukon engineering deserves careful attention, like the video and subscribe to keep tracing how each part worked. That dependence on relationships becomes clearer beside an above-ground log cabin in interior Alaska. A well-built cabin could be durable and warm. Its thermal burden began with exposure. Most of its walls and roof met moving outside air directly. Wind pressing against an exposed wall increased airflow through any unsealed joint. Cold air entering one gap displaced warm air through another. The fire then had to warm that incoming air while replacing heat conducted through the roof and walls. If you picture both buildings in cross-section, the cabin presents more of its boundary to the weather. The Koyukon house reduced that exposure with a compact room and heavy covering over much of the frame. Birch bark and moss would have slowed air movement through the shell when kept in useful condition. Earth added depth and separated much of the inner structure from the wind. The low entrance passage also prevented the occupied room from opening straight onto the weather. Those materials did not produce heat. They changed how quickly existing heat could leave. When the shell and entrance geometry reduced loss, the hearth faced a smaller demand. A more exposed building needed stronger or more continuous heat production to balance faster exchange. The heavy covering also changed the timing of that exchange. Its mass warmed and cooled more slowly than a thin exposed surface. If you watch the fire through the night, its output rises after fuel is added and falls as that fuel burns down. A lightly protected interior responds sooner. A heavy shell delays the change at the occupied surface. That delay did not remove the need to tend the hearth. It gave the family more time before a smaller flame produced a colder platform. If you remove the shell, the fire must replace energy faster. Open the entrance straight into the room, and the draft reaches the occupied band. Lower the platforms, and bodies enter the coolest moving air. The roof opening shows the same balance. Closing it would retain some warm air briefly, but smoke and combustion gases would lose their defined route. Enlarging it would release those gases more freely while carrying more warmed air outside. Its value came from its position above the hearth and within the full circuit. If you trace the house from outside to center once more, the full circuit remains visible. Wind meets a deep covering rather than a thin exposed wall. The entrance turns and descends before reaching the room. Replacement air arrives low. The central fire warms it. Heated gases rise toward the roof opening. Platforms hold people between the lower draft and upper exhaust. This reconstruction does not describe every Athabaskan community or every winter dwelling. It follows the Koyukon arrangement used here. The important point is how the documented parts interact. Each relationship reduces the burden carried by the next. You can test those relationships by removing one at a time. Increase leakage and the hearth needs more fuel. Move the draft across the platforms and bodies lose heat faster. Block the high exit and smoke spreads through the room. Keep the relationships intact and a modest flame becomes one part of a larger thermal system. Outside, winter air still presses against the covering. Snow gathers over the roof. Wind crosses the river country and the temperature continues to fall. Inside, you see the result in ordinary actions. One person places a piece of wood on the central fire, then returns to the platform. Another finishes repairing a strap without holding stiff fingers over the flame. Damp clothing hangs where warmth can reach it. Colder air remains near the lower entrance and floor. This arrangement belongs to Koyukon Denaa building knowledge. It connects material choice, room shape, fire placement, and daily use within one working environment. The credit belongs in those exact relationships, developed for life in Alaska's interior. Birch lowers the ember orange pencil from the diagram. He closes the field notebook and rests the pencil across its cover. The weather outside has not weakened. The house has not removed winter. It has changed how quickly winter can reach the people inside. At the center, the flame settles to a low glow. Conversation continues. Hands keep working. No one needs to feed the fire again yet. Outside, the cold keeps taking heat. Inside, the family has time.